Our aim today is to talk about dilating figures. I want you to think, and you can raise your hand silently. I don't need any verbal responses here. Raise your hand if you have ever been to the eye doctor. That's the type of verbal response I do not need. Raise your hand if you have ever been to the doctor. The eye doctor. Keep your hand raised if they've ever put those drops in your eyes that sting really, really bad. And then afterwards, you can't see very well, and they sometimes give you these sunglasses looking things because everything seems so bright. Okay, so a lot of you have had this experience. And as Precious has told us, that process is called dilating your eyes. Now what actually happens, here's a little biology lesson for you. Those drops create a response in your eyes that cause your pupils to dilate, which means get bigger in this particular case. However, an actual definition of dilation doesn't necessarily mean that it gets bigger. But let's think about your eyeballs for a second here. When your pupils dilate, do they change shape? Are they going to change from a circular shape?
To a heart.
No, they just become a bigger circle. And so that's the idea of what a dilation is. It is a change in the size of a shape, but not the shape itself. We're going to talk further about similar figures in a minute. We're going to talk a little bit about that today, and then we're going to spend even more time on that later. But this idea about dilation, if you can remember that example, dilation means that we're just changing the size of the shape. Looking back at this figure, it tells us that this figure is dilated using a scale factor of 2, right? The original points and the new points. So we have the original points here. These are pretty easy to pick up. 2, -1. 2, -4. 5, -1. And 5, -4. So we have a scale factor of 2. Let's talk about scale factors. Scale factors are multiples used to increase or decrease size. As an example, for instance, I might have 3 inches of string, and I may say that I want to make my string 3 times longer. That is a scale factor of 3. I want to increase by a multiple of 3 the length of my string. We can do the same thing with figures. I want to increase the size of my shape by a scale factor of 2. I want to double the size of my shape. Now, how can we do that on the coordinate grid with our coordinate pairs? It's really easy with a rectangle because we recognize the lengths of this particular size. But if with other shapes, it may be more difficult. Here's what we can do. We can actually take each point, no matter the shape, and multiply it by our scale factor. So my scale factor is 2. That means I'm doubling the size, and I can do so by multiplying everything by 2. 2 times 2 is 4. -1 times 2 is -2. 4, -8, 10, 10, -2, and -8. And these would be all of my new points. And according to my hypothesis, my explanation, that should mean that whatever shape we get out of this is going to be twice the size of the original shape, but still be the same quote-unquote shape. Okay? It will be similar. Well, let's go ahead and graph these to figure it out. 4, -2. 4, -2. This is where my A prime is supposed to be. And 4, -8, that's where my B prime is supposed to be. C prime is supposed to be at 10, negative 2. And my D prime is supposed to be at 10, negative 8. Are these two shapes, my original figure in black and my new figure in red? So these shapes do indeed look like they are approximately the same size. Now, when we come down here and we look at this, we talk about the ratio of the sides, all right? The ratio of the corresponding sides. Our definition of a similar figure is a shape, two shapes, whose corresponding sides, that means the sides that quote-unquote match up, corresponding sides all have an equal ratio. As an example of that, we're looking for the ratio from the original AB to the A prime, B prime, the new AB. So if we go back and we look at this and we want to look at how long those sides are to see what the ratio is between those sides, I can go back and count. My original AB is 1, 2, 3 units long. My original AB is 3 units long. And my A prime, B prime, that's the AB of my new figure. I can count over here is 1, 2, 3, 4, 5, 6 units long. And so I can see that the ratio is 6 to 3, which if we simplify is 2. And this makes sense. We were indeed supposed to be doubling the size of our shape. If we go around and we look at all of the different sides of the different shapes, they should all have a ratio of what? 2. And that's our definition of similar figures. We're going to be spending more time on similar figures later. That's not the key piece of today's lesson. However, it is a piece that if you have it, will be much easier for you to capture similar figures later. All right, the second problem. So we proved that this worked just fine to multiply all of our coordinates when they were all in the same quadrant. However, when they're in different quadrants and they're crossing over the x-axis, y-axis, this seems like this would mess some things up pretty significantly. So let's go ahead and try it the same thing here. Let's write our original coordinates and our new coordinates, and let's see if we still get that same scale factor to come out the way it's supposed to. All right, so I'm just going to do this while you're doing it. I'm writing my original points. It tells me the scale factor is 2, so that means my multiplication is times 2 on all of these. And then I'm going to go ahead and graph them, all those new points. So, kip yes or kip no? Did our figures turn out to be similar?
Yes.
Yeah, these look like they're the same quote-unquote shape, just different sizes. Let's go ahead and check the ratios on a couple of the sides here. So we have AB, the original AB here was 3. The new AB is 1, 2, 3, 4, 5, 6. That looks like that kept our scale the way that it was supposed to, because we were supposed to go from a 3 to a 6, so our A prime, B prime, which shows us our scale factor of 2. One thing that when we're talking about scale factors, it's a lot like change in y over change in x, where we think about y as kind of being the output of that equation, and x being what we're starting with. It's the same thing when we think about scale factors. We usually think about them as this is the new over the old. Okay? That's going to help you with tomorrow's lesson if you already have that in your brain. So, does crossing over the axes mess up our rule?
No.
No, everything worked out just fine. Silali. So, moving forward, now we have one that says it's dilated 150%. And so this doesn't give us a scale factor like the original did. However, we can turn that 150% into a scale factor. What do you think the scale factor, the equivalent scale factor for 150% is going to be? What is our equivalent scale factor going to be for 150%? What do we think? Isais. Why do you think that? Yeah, so we think about scale factors as being something we multiply by, and if we want to make something 150% of its original size, or any percent of its original size, we know we multiply by that percent by changing it to a decimal, 1, 2. So this is the equivalent of a scale factor of 1.5. And this should make sense to us because when we're trying to find a percentage of something, we're multiplying it. It's the same idea. Scale factors and percentage of originals. Yes, ma'am.
So what we're doing, like how it said, well, just how we're doing it now, like we still won't, we won't see no more how we turn into like, you know how it used to be. Oh, we used to turn into like 150. Come on.
1.5.
So since our equivalent scale factor is 1.5, we can multiply everything here by 1.5. So that's going to give me my new coordinates for A is negative 1.5, 3. My new coordinates for B, negative 1.5, negative 1.5. And C as 3, 3. So let's go ahead and graph all 3 of those points. Negative 1.5, that means backward 1.5, then up to 3. So that's going to be between 1 and 2 on my y equals 3 line. And my next point is negative 1.5, negative 1.5, so that means over 1.5 and down 1.5. That ends up between our 1 and 2, our negative 1 and our negative 2. So this is my B prime. Didn't seem to move very far. And our 3 over 3 for our C prime. And so what we can see is that with this, yes, we increased the size of this shape, but not by very much. What do you think changes how much we increase the size of a shape? Yeah, the scale factor that we're working with. The bigger the scale factor, the bigger that's going to make the shape. And that makes sense because we're multiplying it by larger and larger numbers. So when we see a scale factor of 1.5, we're going to know that that's going to be relatively close to the original. Whereas if we see a scale factor of 5, we're going to say, wow, that's making it 5 times bigger. All right, so when we look over here, what happens when we have scale factors that are bigger than 1? If we multiply by something that's bigger than 1, that's always going to make the numbers bigger. So that means our figures are always going to get bigger. So we should be able to make a guess about this next problem where we see the dilation is 50%. We're going to dilate it to 50% of the original. Our dilation, our scale factor, our equivalent scale factor for 50% is what? Blanca?
0.5.
Yeah, 0.5. And so we're going to be multiplying by something that is less than 1. What should we expect to happen to our shape? Najari? By multiplying by the 0.5, what should I expect to happen to my shape?
For it to go, it's to go around the coordinate. Get bigger. Get smaller.
We're multiplying by something less than 1. What would we expect? Alejandro? Smaller. That's multiplying by a fraction. That's going to make our number smaller. So our scale factor, we should think that it's going to be less than 1. It's going to get smaller. Well, let's see. Get all of my original points over here. -2, 6, -2, 2, 4, 6, and 4, 2. And my scale factor is times 0.5, so I'm multiplying all these by 0.5. If I'm multiplying by 0.5, what fraction am I multiplying by? Anadari? Jamari, what fraction am I multiplying by if I'm multiplying by 0.5? And multiplying by 1/2 is really the same thing as dividing by... Multiplying by 1/2 is the same thing as dividing by... Hold on. I have some number x, and I'm multiplying it by 1/2. Top times top, bottom times bottom, that's like x/2, which means multiplying by 1/2 is the same thing as dividing by...
2.
I'm glad to hear that at least 3 people in this class have a functioning brain today. Anytime you multiply by any fraction, 1 over whatever, it's like dividing by that whatever. So, multiplying by 1/2 is the same thing as dividing by 2. Multiplying by 1/3 is the same thing as dividing by... Multiplying by 1/4 is dividing by... Multiplying by 1/8 is like dividing by... Multiplying by 2/3 is like dividing by...
0.75.
3/2. 3
Yeah,
times.
tricked you.
Ha, I got it.
Alright, it's by like 0.6 repeating. Alright, so multiplying by 1/2, now I'm really just dividing by 2. That makes this really quick. And I'm going to graph my new shape. -2, 3. Oops, that should be -1, 3. -1, 3. -1, 1. Two, 3. And 2, 1. And sure enough, we see the same shape. And if we wanted to check if it was similar, we check that the ratio on all of them were the same. So our ratio on our original, we have a 4, and its corresponding side is a 2. So 2 over 4, that is 1/2. If we look at the bottom, the original is 6. The corresponding bottom is 3. I get 3 over 6, which is 1/2. And so as we go around this figure, we can prove that it's similar by showing that all of the corresponding sides have the same ratio.